Welcome again to the NPTEL course on storage systems. So, I think basically to summarize, we looked at some aspects relating to consistency, some commit protocols. Then we said we had to address some issues like distributed locking, scalability, reliability, etc. So, today we will try to take a look at this part, scalability, reliability. We took some notice of this particular problem in the previous class. I think we will revisit again later, but right now let us look at these two parts. Okay. So, as a way to address this issue, I thought we started looking at this, and I want to really today talk about one good example of a reliable and scalable system. This is the Google file system. Okay. One can say that this is, as far as I know, this is the largest file system to date. I am not sure if Facebook, what exactly their system, the size is, but at least for some time at least, Google file system was the largest file system. So, we will try to look at how the design of this, and this particular file system will look into some detail. So, we will at least take 2 or 3 classes to go through this, okay, because we go into some reasonable detail. We have not really examined any file system in sufficient depth. So, I thought I would take Google file system as an example. First of all, this Google file system is a non-POSIX system. Okay. That means your application has to be aware that it does not have the kinds of things that a POSIX file system will support. For example, the semantics of like deleted but open files, all those things are certainly not going to be supported here. Okay. The most important thing is it has to be scalable, distributed, and for data intensive applications. Critical things are performance, scalability, reliability, and availability. Performance, because this particular file system is supporting one major application, that of searching the web, and since the critical part of this service should be highly performant. It should be able to supply the search results fairly quick in spite of the massive amount of data that is there. So, performance is very critical. Scalability, because the web is growing at a very high rate. I am pretty sure that when the web started with 94 or something, probably you could have got some hundreds of megabytes and of course taken care of everything. Very soon it became gigabytes and terabytes and petabytes. Okay. Now it is certainly in multiple petabytes now, tens of petabytes. Reliability, because there are so many disks, so many components, the chances of it working completely correctly are extremely small. So, we need to make sure that the system is reliable. It has to be available, because otherwise the search service will be unavailable randomly, which is a problem. Okay. So, it has to be highly available. Most important thing is it has to have high aggregate performance to a large number of clients, okay, because the population which is using the Google file system could be at any point in time for multiple millions, okay, tens of millions. So, you need to figure out how to supply this, okay. And sustained bandwidth is more important than low latency. Okay. This also is important, low latency, but critical thing that they have tried to do is to have a sustained bandwidth from the file system. The low latency is handled through some of the mechanisms. Okay. For example, by using certain parts of the system to operate from memory, to replicate various other things. Okay. But the file system per se, the more important issue is sustained bandwidth. And one other important thing about this file system is that high fault tolerance to allow inexpensive commodity hardware. This is a very critical part of the design, because when Google started out, they were a small company, they did not want to go for extremely expensive commodities, expensive storage systems. For example, if you go with a storage area network, it is going to be fairly expensive. Okay, they didn't want to go that route. They wanted to do it slightly cheaper. Okay. So, the idea here was to find a way of redesigning application and file system together, so that you can use fault tolerance to be able to use inexpensive commodity hardware. That is the basic thing they tried doing, and I think they succeeded quite well. Okay, let us try to understand what they did and how they did it. Notice that this is slightly different design space than small businesses or let us say enterprises, because they do not need a distributed file system per se. They can deal with reasonably centralized types of systems. There is certain interest in performance, and they are interested not so much in scalability. I think it is not, they do not grow that rapidly. It is okay. I think they, some of them might, but many of them have, they grow in a sort of 10% growth per year, which is sort of tolerable. You can handle it. Okay. So, they might not require this. For example, you do not need to scale from gigabyte to petabytes, that they might not, that might transfer, some might not be needed. Okay. So, for those kind of systems, I think well engineered SAN solutions could be useful. Here the design space is different. So, the idea was to take inexpensive commodity hardware and somehow marry it with a well designed, highly fault tolerant system, so that the fact that it is inexpensive or it is not specialized components can still deliver the goods. Just to understand what we mean by inexpensive commodity hardware, you will see that in the case of disks, you will find certain gradations. You can find what are called enterprise disks or the common non-enterprise or consumer disks. Typically, the enterprise disks are much more expensive. They are carefully selected for vibration tolerance and various other kinds of things. Whereas inexpensive disks, they are let us say they are not checked for some of these things. So, idea is to say that let us use inexpensive disks or inexpensive components in general and build a highly fault tolerant system, so that you can get the design space, the design you want. Okay. So, one of the important assumptions in this particular file system is component failures are the norm rather than exception. Okay. And it can be due to many reasons. It can be because of bugs in applications or operating systems, kernels, wherever. Okay. Human errors, failures of disks, memory, connectors, networking, power supplies, all kinds of things. Okay. So, the only solution to this problem is to constantly monitor things, do error detection, fault tolerance, in case things go bad, automatic recovery, okay, etc. All those things are absolutely critical. Okay. So, if you have very large file system, very large system spanning the web, and so it is basically you need to do this somewhat systematically. So, what we will do is we will start looking at some of these aspects. So, what is the high level JFS design goals? It was designed for Google's application workloads and current technology, and possibly try to accommodate future trends also. Okay. That is what they try to do. So, let us look at one major decision that they took. Modest number of large files. Okay. We are not talking about trillions of files. We are talking about millions or slightly closer to hundreds of millions of files, rather than trillions or 10 to the power 15 times of files. That because the web is big, so you can in principle imagine that there are trillions or hundreds of trillions or even more of files. But they decided that is not the right way to do it. They decided that we will have a modest number. What I mean by modest is hundreds of millions or about billions. Okay, not much more, not in terms of trillions or even 10 to the power 15 times of files. Okay. And large files, yeah, 64 megabyte each. Okay. So, basic idea is that if you go for large files, it is good for scans, streams, archives, and what are called shared queues that are there between producers and consumers. Basically, oftentimes what happens is that you are searching for something and you want to do what's called scans. And if you are able to get a large file in place, you can do much better when it comes to read ahead, all those kind of issues. Okay, it comes out to be much better for scans when you have a large file than scattered files here and there. Lots of times data is produced in streams, so I want to be able to I'm going to access them in a particular sequential manner typically, so writing it in large files is useful. Archives by definitions are large and they are also sequentially written or read. Okay. So shared queues are those systems by which multiple producers and consumers can put stuff into a particular file, and so this also requires large files typically. Okay. So one basic, and this, you can see that this is quite different from a regular POSIX kind of file system that we use normally. The file system sizes are not 64 megabyte. Typically, we assume that it is closer to, let us say, multiples of 4 kilobytes or 8 kilobytes. Only nowadays, with widespread use of music files like MP3, the size of files is a typical file that most people are nowadays using, because a lot of people are listening to music, is closer to 4 to 8, 10 megabytes, that kind of stuff. But in the past, before the music files became common, most of the design space was to handle 4 kilobytes or 8 kilobytes or somewhere in that region. That is the size of the file, typical file. Other difference is that append new data is common, not overwriting existing data or random writes. So basically, you are adding new data rather than modifying data. Okay, that's why it is designed for handling appends better than overwrites. Okay, and they do a lot of performance optimizations for appends, and also they give you atomic guarantees for appends. That is, when you are concurrently appending, multiple parties are appending at the same time, then you want to give some atomicity guarantees. Okay, so they are designed a specific operation called atomic append, so the multiple clients can append concurrently to a file without extra synchronization. I think this is somewhat similar to if you have studied computer architecture. There is, you have some synchronization sometimes you have to do. It turns out to be expensive. Sometimes people have come up with slightly different models of synchronization. Like for example, you might have come across fetch and add. A fetch and add, it allows multiple increments simultaneously, and then each client will get a consistent version of how it was added to that shared variable. Okay, everybody gets different values, but they all happen in some order. It's not guaranteed which order it happens, but everybody gets some serialized version of the adds, and each one of them gets a distinct value of the add. Here also similarly, what it means here is that any number of people can be trying to append. You get some serialization of the appends, some serialization. We don't guarantee which one it is. Okay, and but everybody sees that they appended a particular offset. Every party gets a different place where they appended. Okay, so that way you can essentially, you don't need any extra synchronization. You just can go ahead and start appending, and the file system is taking care of it. Okay. Again, because you are talking about a large files, it makes no sense to cache them, because by definition, if you have a large file and you are doing mostly scans and those kind of things, the LRE part of it is quite doubtful. The best is not to do any caching of data blocks. You just pick up big chunks, use it, and then let us say throw it out. Actually, there is some caching going on, but this is below their GFS file system, because they use Linux as a node where the GFS is working on top of it. So those caching that happens happening through Linux, not through GFS. Okay. They also have a fairly relaxed consistency model. We will discuss this again with respect to appends. This is quite an important aspect of the design. We will look at this particular consistency model also. And fundamentally, as we discussed earlier, this is a cross-layer design of both the applications which are going to use this file system and the specific file system capabilities that are there. It is basically, they have designed the file system API knowing fully well what kind of applications will be targeted. Of course, this is in any evolutionary system, the set of applications keeps changing, but they had a certain idea about the kind of applications they wanted to target, so they attempted it. In retrospect, some of the design decisions, especially supporting only large files, it has been found to be problematic, and they are actually revisiting these issues and they are changing things here. Okay, they have changed quite a few things, in some areas here. Okay, again, we will at the end of this particular discussion on GFS, we will study exactly the kinds of problems that GFS has encountered, and then the kind of remedies that people are looking into. Okay, we will just look at that also. Most important thing is that it is a cross layer design. Okay, what does it mean? It means that knowing fully well the application space, the kind of applications that are written, you try to tailor your file system API for those kind of things. Okay, so that there is some synergy between both these things. Whereas POSIX, for example, is a general purpose thing. It doesn't. It has certain model of applications, but typically desktop applications. Okay. So its design space point is somewhat different from what these people were trying to do. Okay. So we will also look at how this is done. Okay. Again, we looked at this figure in the very first lecture, I believe. So again, we will just quickly look at what is going on. You have an application, it could be a search application, for example, and basically the application talks to the master. There is a single master, and we will not discuss this right now, we will just think about it later. A single master to make to avoid consistency issues. Okay. Single master, and an application will ask details about a file's chunk locations. Okay. That is what this is. Basically, the application tries to figure out a given file is chopped up into multiple chunks, and they are stored at multiple nodes. And the first thing to do is, if there is a file, you talk to the master and find out where the chunks are, and the application can directly talk to those chunk servers without going to the master to get the file chunks. And because of reliability reasons, we need to have some replicas, and they are done replicas. For example, file 1 chunk 1 is also replicated here, file 1 chunk 2 is replicated 3 times, this is 2 times, etc. Okay. So, it is roughly the high level design. We will go into more details soon. Okay. First of all, it does support a certain set of common operations that everybody uses when they use a file system, like create, delete, open, close, read and write, but it does not support all the POSIX ones. Even the semantics of all these things also is quite different. For example, at least in the written documentation I have seen about GFS, they never talk about a link, for example, command, a link or a symbolic link or whatever. They could be having it, but it's not, I have not seen it. Okay. So, those things are all you can call it if you need to have those things for POSIX compatibility. Okay. They also have certain other types of operations. For example, you can create a snapshot. The idea being, you want to be able to take some kind of a copy of a file or a directory at low cost. Usually this is done through what is called copy and write. Okay. It is not really a physical copy, it is basically a logical copy, and so there is sometimes you can take a snapshot, so that you want to be able to see a particular file or a directory as it exists at a particular point in time, and then, but this particular operation has to be low cost. So, for it to be low cost, you have to use some techniques like copy and write, otherwise this is not a feasible solution, okay, because the directory can be quite arbitrarily large. Okay. As I mentioned already, they have some specific design components for handling appends, and it has to be atomic in spite of multiple clients. Okay. This is one other critical thing that they provide. Okay. So, again one critical part of the GFS design is it is a single master, okay, and multiple chunk servers and clients. Okay. There are any number of clients, there are multiple chunk servers, but there is only single master. Okay. And all these things, whatever stuff that is running on all these machines is all user level server processes on Linux. Typically, you will find that the file system is in the kernel, especially at the desktop, but here is a case where everything here is user level, everything is running on Linux, okay. And they are essentially using Linux as a platform on which all these masters and multiple chunk servers clients are all running on top of it, okay. So, files are divided into fixed size chunks and each is identified by an immutable and globally unique 64-bit chunk handle assigned by master chunk create. So, when you create a chunk, you have a unique name for it and it is not reused again. So, I guess it is 2 to the power of 64. So, it will run out someday, but looks like it will be not soon, okay. So, that is why they can handle this, okay. So, chunk servers store chunks on local disks as Linux files. So, various chunks are there and each of them gets a number that basically that unique 64-bit chunk handle, okay, and that is how they are numbered as and they are stored as Linux files, okay. So, each Linux is basically, each chunk is basically a file name with a unique chunk handle. So, when you want to read or write a chunk data, right, basically what you have to do is you have to specify a chunk handle and a byte range, okay. So, if you look at NFS, there it was a file handle and a, what is it, the offset, right. Here basically what you have, you do a chunk handle, okay. So, again for reliability, each chunk replicated on multiple chunk servers, typically 3 replicas is default, but you can have different replication levels for different parts of the file namespace, okay. It is up to you to decide. So, let us just quickly look at how this works. So, the application, there is a library by which the application can make calls to the GFS client, and first you request a file name and a chunk index. It goes to the GFS master and this GFS master, given a file name and chunk index, it gives you a chunk handle and a chunk locations where they are present, okay. So, basically you are essentially saying, given a name of a file and which chunk you are interested in, right. Then the GFS master will give you a unique set of a unique name for a particular chunk and where they are located, because it is replicated. There could be 3-4 places where it is replicated, you get the locations. Now, you basically take the chunk handle and the byte range and send it to the GFS chunk server, okay. And then the GFS chunk server talks to the Linux system below it and then it uses a regular local Linux file system to pull out the chunk and it goes into user space process and that is basically copied out to chunk data and then sent out to the GFS client from where the application gets it, okay. Here you find that the GFS master has complete control over that file namespace, essentially the directory structure, and it also keeps track of the metadata corresponding to where the chunks are, okay. So, there is a table which is file to chunks table, okay. So, again there is some communication between GFS master and chunk servers. I have listed only one server, chunk server, there are many of them, okay. There is only one of this and there are many of this, there are many of this, but there is only one of this, okay. So, there is some communication between the GFS master and multiple chunk servers with respect to state, etc. Okay. This is roughly the high level idea about the system. The basic idea is that you go to the master with a request about where the chunks are located, okay, and you also get a chunk handle, okay, and then you go to the chunk locations and present the chunk handle and you get the data back, okay. Let us just see one of the important design aspects of this large chunk size. As I mentioned, this large chunk size has certain difficulties. We will discuss it later what the difficulties are, but in their design they decided that it was good because it reduces clients need to interact with the master, because if you bring it in one big shot, then you do not have to keep interacting with the master, because there is only a single master. If you keep on interacting with the master, then the master will be overloaded, okay. So that is one part of it, okay. So if reads and writes happen to be on the same chunk, then of course only one request to master for chunk. Basically in some sense there is read ahead going on in some sense, okay. Also reason being applications mostly read and write large files sequentially, okay. For small random reads, client can cache all chunk location information even for a multi-terabyte working set. Because the size is big, you can cache all the information even for a multi-terabyte working set, okay. Because each chunk is big, 64 megabyte. So the number of even if a multi-terabyte working set, the number of chunks is going to be manageable. It might be in the region of, let us say, if not about millions at the most, okay. And if you have a million kind of chunks, right, if you have a multi-terabyte working set, if you have a million, let us say, chunks, each chunk location information, let us say, is some tens of bytes, then it is still feasible for you to cache it, okay. It is definitely possible to cache it, okay. So again, there is other reasons also why this is useful. With a large chunk, the client is likely to perform many operations on given chunk, and there are issues about networking also which makes sense, because you can have a large persistent TCP connection for a longer period of time, okay. It helps in the efficiency of TCP itself, okay. Most important is you have a large chunk size, it reduces the size of metadata on the master, and actually now we have the luxury of keeping all metadata in memory. Again, we will look at this in some detail. This is one of the critical aspects of the large chunk size. You basically can keep all metadata in memory. Once you keep all metadata in memory, then you can do lots of interesting things fast in memory itself, okay. You want to rebuild something, everything is in memory, okay. So it is fairly quick, okay. You are not now limited to disk speeds, okay. So in one sense, large chunk size is connected with all metadata in memory, and it turned out the current technological solutions, it made it possible, okay. The same design would not be feasible some other time. Nowadays memory is reasonably cheap, therefore this is a sensible thing to do. But there are some, at the time when they designed the system itself, they came across certain problems. I will later talk about the kind of problems that exist as of now, okay, because this was designed about 2000 or slightly earlier, okay. At that time itself they came across certain problems, but post this particular paper was published in 2003, SOSP, all the details, and around that time already they had seen some problems, but later also there are some other problems which the designers have come across. We will discuss it later, exactly the kind of problems they came across. What is one problem they came across at the design time itself, okay. Suppose you have an executable, it is a very popular executable, okay, and it is small enough that it fits into one single chunk, okay. Then it turns out that if there are many clients wanting to execute that particular popular executable, then all of them will start going after that particular node with that particular chunk, okay. So that is why they essentially had to ensure that popular executables are given higher replication factor, okay. And also when applications are getting started, you make sure that there is some kind of back off, not everybody starts at the same time, okay. You need to ensure that even if there are 100 clients wanting to, when they just started, let us say there is some system and all the clients start at the same time for some reason. Okay, means all the go try to get it from one node. Okay, then you will get some overload of the particular system. So one thing to do it is to somehow recognize the situation and stagger how they actually access it. Okay. Of course, the sensible thing would be to have some kind of a tree structure. So if one guy has got a copy, some other guy should be able to get a copy from there. So you basically create a, instead of going to the same guy, if you have somebody has read it, some other client has read it, other party should be able to get it from the other clients rather than directly from the node that has the chunk. Okay. So but this they decided was too costly, they have not done it. Okay. It's possible one could think of doing it. Okay. They have left it as a possibility. Okay. Again, as we mentioned before, this GFS is a user level design. So GFS client code is linked into each application. Okay. That implements the file system API. So this client code communicates with master and chunk servers to read write data on behalf of application. Okay. Again, this kind of design has been attempted in other areas. For example, if you have parallel file system, you find that this kind of design is quite common also. Okay. And the reason why that is useful there is because if you do it at the user level, then you can do what is called user level networking. So it doesn't go through the, you don't have multiple copies if you go to the kernel. Okay. So we can have also a user level file system where things are directly mapped across the network interface cards, so that you can avoid the copies and touching of all the data by some other kernel code. Okay. So this is not an unusual design. It is many people have done this. Basically, the fact that the file system actually is in user space and the client code actually is linked into each application. So the clients interact with master for metadata operations, and these metadata are cached for small periods of time. Again, just like NFS, there is some element of caching that goes on, but it's only for metadata. So there are still, here also there are some issues of consistency. Basically, they have a timeout mechanism, but it's possible that you can indeed get into the kind of problems NFS had. But the applications are aware of all these things. It's not as if, as mentioned in this particular system, the application has been designed fully knowing what the file system is capable of doing. It's not like a POSIX system where the application is written in a POSIX model and the file system has to implement it. Here, the application has to take the trouble to figure out what the file system is doing. Okay. So clients interact with master for metadata operations, but all data bearing communication direct to chunk servers. Okay. The most important thing is not this, since there's a single server, you don't want all the communication to go through the master. For example, here, if you think about it, right, you don't want all the data to go through this. You want to get the metadata here, this side, but once you got the metadata, you want to directly go to chunk servers. You don't want to go through the master. Otherwise, this will be a single serious bottleneck because there's only a single master, okay, only a single node. No caching of file data by client or chunk server, but clients cache metadata. Okay. Okay. So the chunk server, which is a user process, does not need to cache file data, but they may already be cached as local files in Linux buffer cache. Okay. The cache server, this is as mentioned, this is a chunk server is basically a user process, and it's not doing any caching of anything. Okay. And it may be there as local files in Linux buffer cache. Okay. Each chunk replica stored as a Linux file on a chunk server and extended as needed. Okay. Now, as I mentioned, it is 64 megabytes. Each chunk is 64 megabytes, but they do what's called lazy space allocation. So it's essentially, it's given space, but it's not all allocated. It's that in some sense means that it's not backed by disk. It is notionally there, and that's lazy space allocation avoids space wasting due to internal fragmentation. Because it's another critical part of the design. Okay. But this is makes it slightly more complicated also. Once you have lazy space allocation, then you need to have some other metadata to keep track of the fact that you don't have it, and you have to allocate now and then, and the blocks may get scattered here and there. Those kind of issues also will crop up, because when you're trying to get blocks at the time when you want it, it may not be contiguous. Okay, so there could be some issues here also. Okay, but if you are by definition dealing with large files, right, you will be requiring in large requests also will come. So then that fragmentation or the scattering of files is likely to be also less of a problem. So let us just look at the GFS metadata management. So the one important thing about this design is the master maintains all file system metadata, all of them. Okay, the file and chunk namespaces, for example, all the file, because there is going to be a directory structure of all the files, etc. That metadata for all the files, file structures, they will all be sitting out here. Same thing about chunk namespaces. Okay, basically a file has got multiple chunks. Somebody has to keep the track of which file, what chunks are there in each file. Okay, that's mapping from files to chunks. Again, things like access control information also has to be kept here, and current locations of chunks replicas. All the metadata is eventually kept here. Okay, so because only master keeps it, there is no need to have any distributed coordination. That makes it that simple, right? So that's why the single master design is well known to be a single point of failure. If the master dies, everything goes down, right? But they decided the single point of failure problem is serious, but you get so much advantage by not worrying about this aspect, okay, that you can probably do better. Okay, so I think that's one of the reasons why they have gone for it. There are certainly problems. That's why there is. We'll come to how they handle the single point of failure issue later, okay, by having the shadow master, etc. Okay, we'll talk about it later. Okay. So because you have only one place, it's easy to do system-wide activities, okay, in a simple way, because everything is happening in a single place. The full state of the system is known to the master. Okay, so it's somewhat easier to design the algorithms. For example, chunk lease management, garbage collection, orphan chunks. Okay, we'll come to why this happened later. Okay, chunk migration between chunk servers. So this part of it we'll discuss it later. All these things later. Okay, so other thing it also does is it keeps track of all the chunk servers that are, whether they are alive or not, by sending heartbeats. Okay. So basically the reason why everything is in the master is because single master makes design simple, better chunk placement replication using global knowledge. The global knowledge, everything is sitting in one place, so it's somewhat easier to do it. Okay. Okay. Let's look at some other design aspects. Okay. Master does not store chunk location information persistently. Okay, everything is sitting in memory only. Okay, means the basic idea here is that the division of labor between master and chunk server. The chunk server is the party who actually stores things, so he is it's a better entity which knows about what it's storing rather than the master. Master can always get the stuff from chunk server. Okay, that's the idea. So basically, when each chunk server comes up, right, it can figure out what chunks it has got, and then whenever a master starts up, it can request all the chunk servers to tell them what it has got. Okay. Again, whenever a chunk server joins the cluster, you can ask the chunk server to supply the new information, because the chunk server is sitting on a Linux system and it has persistently kept information about all the chunks it has got. So whether it has crashed or whatever, it can always come up with its set of chunks it has got. Okay. So whenever a chunk server joins the cluster, it will request, the master will request chunk server to supply whatever chunks it has got. Okay. And then, so as long as it tracks each of the chunk servers, whether how they come in and how they go out, right, it can always keep a consistent notion of what chunks are present with. Okay. So basically, it controls all the chunk placement and monitors chunk server status with regular heartbeat messages. So, it exactly knows who is out there, and since it manages all the chunk placement, it knows exactly what is happening. Okay. That is why it does not need to keep chunk location information persistently in its own node. Okay. Whatever it keeps, it is kept in memory. Okay. So, it is very fast also in terms of supplying information. Before this, they actually were storing it persistently, and that created lots of problems. What is the problem? You have to maintain consistency between what a chunk server thinks it has got and what the master has got. Okay. You need to keep on reconciling these two notions. That is a bit of a problem. Okay. And because chunk servers join, leave the cluster, change names, file, restart, whatever they are doing, they can do all kinds of things. Okay. And the basic argument why this makes a lot of sense is that a chunk server has final word on what chunks it has got. Only it knows, nobody else can know. Precisely because you may find that a chunk server there might be some errors on chunk server, and suddenly certain disk may go bad. Okay. Only the chunk server which is attached to that, which is running on that Linux system, can figure out what is going on there. Because normally these chunk servers, they are running on some nodes, and that node might have multiple disks, 2 or 3 or 4 disks. So, any particular disk can go bad, and this is completely local events which the chunk server can track. So, even if it has in the past had some chunks, suddenly it may disappear, and only chunk server knows about it. Okay. And so, it may be better for chunk server to keep track of this and let the master get the information from the chunk server. Okay. So, they redesigned this particular aspect to not keep it persistently. Another next issue is, as I mentioned before, all the metadata is memory based in the master. Okay. So, therefore, it is easy and efficient for master to periodically scan its entire state in the background. Okay. It has to, for example, we will look at how some chunks become garbage. So, if chunks become garbage, you have to do garbage collection. Okay. So, all these things can be done in memory. You do not have to do it on disk. So, it can be very fast. And if there is any chunk server failure, you might want to again replicate whatever has been lost on some other machine. Okay. So, for doing all this kind of stuff, you will find that information being presenting in memory is useful. Okay. They also might want to do chunk migration to balance load and disk space. So, all these things, all the metadata is kept in memory. You can actually, you have a completely consistent global knowledge about where things are. So, you can just do it, just go to memory and pick it up and run some quick algorithms, and it will be very extremely fast. Okay. If you have to do all this in disks, you can be probably having serious trouble, okay, now and then. Okay. The most important reason why this all is possible is because it turns out to be practical. Why? Because for each 64 megabyte chunk, it turns out you need less than 64 bytes of metadata. That means that for 64 terabytes, you need only 64 megabytes. Even in 2000, 64 megabyte was not considered very big. Okay. So, in 2000 decided that if I were able to have a web which is about 100 terabytes, right, I just need about I just need to have 120 megabytes of disk, that is all. Right? That takes care of memory requirement, it is not too huge. Of course, with now the size of the web is much bigger. It is not 64 terabytes or 128 terabytes, it is going to be closer to some hundreds of petabytes. That means that if it is hundreds of petabytes, you are talking about, you scale up this by a factor of thousands. Thousands or even, who knows, probably about 10,000. If you scale up by a factor of 1000, we are talking about 64 gigabyte, which is still quite reasonable. You scale up by a factor of about 10,000, then you are talking about very big memories. Okay, we are talking about half a terabyte of memory or something like that, and that can be a bit costly. But even today it's possible. It's nothing difficult to imagine. Okay, because already many machines come with 96 gigabytes standard. Many of them come with. Okay. So that's the reason why it turned out this design decision was quite practical, and it gave lots of amazing capabilities. Okay. So one other thing what is interesting is that most chunks are full, because they are dealing with large files, okay, and therefore only one chunk at the end might be partially filled. Therefore, it makes a lot of sense to actually there's not too many chunks with incomplete information. Okay, that is not fully 64 megabytes. Okay. So that helps also in terms of reducing the metadata load. So again, they use some other interesting techniques to reduce the file name. Okay, because finally the file names have to be stored on the master, and they make sure that it is not too big per file, and they use things like they can store names with some compression techniques. Okay, so this also helps. Okay. So let us so since it's a file system which gives you some guarantees, as I mentioned, appends are atomic, and but the consistent model is a bit complex. Okay, we'll come to that. But once you try to make things atomic, you have to ensure that operations can be either rolled forward or rolled backwards. So you need some logs. So what they do is important metadata aspects like namespaces and file to chunk mappings, we keep it persistent by logging changes to an operation log on the master's local disk and replicate on remote machines. Okay. So hopefully these things are not too frequent, because you are logging it to disk. Okay. So if a master crashes, you can look up the log and figure out what to do. Okay. Another thing that they do is these logs, they serve as a logical timeline that defines order of concurrent operations. Okay. And basically any file creation or chunk creation, right, they are identified by the time of their creation. So given that a log is basically sequential, so depending on the way in which you order the operations, essentially you get a timeline. Okay. That helps also. Okay. Because we notice that all the metadata operations are getting done on the server only, on the master only, nowhere else. So if you are somehow able to sequentialize it, you get a timeline, automatic timeline. Okay. Now one critical thing is that the changes should not be visible to clients until metadata changes persistent. Okay. Now one thing one should remember is that even though certain things are getting updated, there are consistent versions of the files through checkpoints. So if there are some readers, they can look at the consistent checkpoint rather than the current versions as they are getting updated. Okay. That's the reason why changes are not visible to clients until metadata changes persistent. Basically what happens is that the clients can actually use checkpointed versions of files for reads, and they do not have to look at currently being modified files, appended files. Okay. So there is clients are always able to get some information to keep proceeding. Okay. Of course, the reason why this kind of stuff makes sense is because you are talking about search application where it is not absolutely critical, right, that every single data be available. Okay. There is a tolerance for certain small amounts of lack of completeness. Of course, we do it only for data, we don't do it for metadata. Okay. It's only for data. Okay. So one important thing is if data becomes visible to clients before the metadata becomes persistent, right, then if there is a crash or whatever, right, then essentially you are going backwards in time in some sense. Okay. So, that is basically the, you can essentially lose some operations if that happens, okay, even if the chunks are bad. Okay. So, that is the reason why they have a strict rule that changes should not be visible to clients until metadata changes become persistent. Okay. And then basically we respond to a client operation only after flushing log record to disk both locally and remotely. So, these things are essentially time consuming operations. So, it is a problem. That is the reason why the checkpointing and other kinds of methods actually help you a bit. Okay. Essentially, you are limited, the latency is limited by how fast you can log records to disk both local and remotely. So, it is not going to be something insignificant. Of course, the way they avoid the performance bottleneck is to batch them, okay, and so some batching etc. also happens. This is of course typical of most file systems. Now, when it comes to recovery, okay, if a master fails, you have to replay the operation log. So, it turns out it can take some amount of time because now we are limited to disk speeds. So, to minimize startup time, keep log small by checkpointing master state whenever the log grows beyond a certain size. Okay. So, you have to replay the log, but the thing is you can't play all the operations that are taking place. So, the idea is to do a checkpoint, and checkpoint means that the particular file system is at a consistent state. If you just go back to that consistent state, that means you only have to do a small portion that metadata operation that happened after the checkpoint. That is the only thing that you have to do. Okay. Recover by loading latest checkpoint from local disk and replaying only limited number of later log records. Okay. So, checkpoint is a critical part of the thing. Okay. And again, most important is the checkpoint is like a compact B tree directly mappable to memory. Okay. So, again this is kept in memory itself. Okay. So, namespace lookup requires no extra parsing, speeds up recovery and improves availability. So, they are exploiting the memory design, okay, using the memory as a quick way of looking up things. Okay. It is not on disk. Okay. And the reason of course why this is happening is because we have a lot of memory and it can be used for all these purposes. It is not a design exploits the current technical advantages. Okay. Again, even this checkpoint itself is a problem because it has to be, let us say, it will take time. So, the idea is to switch to a new log file, okay, and create new checkpoint in a separate thread. So, basically in some sense, as you are checkpointing, you create a new log file and new mutations, new changes are taking place in the new log file. Okay. That is why no delay for incoming mutations. Whatever changes, whatever metadata operations are taking place, they are not going to be delayed by this. Okay. And the new checkpoint includes all mutations before the switch. Okay. They claim that it takes only a minute or so for a cluster with a few million files. Okay. When completed, return to disk both locally and remotely, a checkpoint. Okay. So, basically the idea is the checkpoint is going to be in memory, is going to be in disk, but you can map it to memory directly when you need it. So, there is a problem of building a checkpoint, it takes time. That is why you want to have one, while one is being made, the other there is new things are going into a new log. Okay. And if you have to read the checkpoint, you have to take it from disk, but you can map it to memory and you can do all the operations in memory fast. Okay. The idea basically is that you want the on disk format to be similar to the memory format. Okay. If you do that, then there is very little work you have to do to get going. Okay. And recovery needs only the latest complete checkpoint and subsequent log files. And again, checkpoint itself can fail because it takes time, right. By definition, if something takes time, there is a possibility of some error, right. So, failure during checkpointing does not affect correctness. Recovery code detects and skips incomplete checkpoints. Basically, the idea is that whenever you do any checkpointing, you keep adding some inline data in the checkpoint itself, and then when the recovery code comes in, it checks for whether signatures are there. If the signatures are not there, we can figure it out that this is an incomplete checkpoint, something is wrong with it. So all these things are done. Okay, I think I will stop here. I will talk about consistency manager in next class. Okay, so we will look at what is the consistency model GFS has got, why it is a slightly weaker model than for example POSIX kind of models, and why their append, for example, exploits this aspect so that you can get high throughput for concurrent appends. Okay, we will look at that one. Okay. Thank you.